Okay, so hopefully you have had an opportunity to fill out this table, these two tables. Um, I have set these up to be done either on a piece of paper or via a Schoology Cami document, either way. The purpose of this is so you can start to see the trends. We have two different periodic trends here. One is ionization energy, the other is electronegativity. Both of these are instrumental in determining how elements bond to one another. Looking at the trends numerically is going to help you, but we are also going to do this in a graphical context as well, and that will also help solidify these ideas of the trends, ionization energy and electronegativity. So, once you've done that, we can move on. So truly, before we even get into ionization energy and electronegativity, we need to talk about the atomic radii. Obviously, the term radii means half the distance from the center to the outside of a circle. And so when we're talking about atomic radii, that really is the distance between, half of the distance between two adjacent atoms, nuclei. So if you think about two atoms, between the two atoms, that distance, will be the diameter between the two nuclei, and then take half of that, that's the atomic radii. So if you think about this, and this drawing here that I have down here, this trend drawing, basically this says the atom is larger as you go from top to bottom down the periodic table. So it increases in size, and that's because we're adding principal energy levels. So as the atomic number increases down a group, the atoms get bigger because as you do that, each row adds a whole nother principal energy level. Think of it as another whole layer of electrons, a whole nother layer of cake, so to speak. All right. The other trend, which seems weird, is as the atomic number increases across the period from left to right, well, the atom is actually going to get smaller. The atom's going to get smaller because what's happening is you're adding electrons to the same principal energy level, but you are also adding neutrons and protons, things in the nucleus. And that additional stuff in the nucleus pulls in that layer, all right, that attractive force, that nuclear attractive force pulls in those outer layers or those layers of electrons, thus making the atom smaller. So why don't you take a moment, copy these notes, and when you're ready, go to the next slide or restart this. So that last one, talking about adding principal energy levels, we're talking about something that's called the shielding effect. This shielding effect has to do with all these layers of electrons, and what they do is they shield the attractive force of the nucleus, all right, from the outer electrons. So if there's an inner layer of electrons, this inner layer of electrons here, that nuclear attractive force, it has a tougher time reaching these outer electrons because what you have happening is these inner electrons, all right, there's some repulsive force going on, and because repulsive force, it repels the nuclear attractive force to the outer electrons, and so that's what we're really talking about, shielding effect. Okay, there's two different pictures here, all right. This one over on the left says the electrons on the outside have no effect on the nuclear charge. The electrons on the inside, all right, they have some attractive force. So we're talking about this electron out here. It has all the electrons on the inside that are running interference for this nuclear attractive force for that particle. So again, copy these notes. All right, ionization energy. Ionization energy, like the definition says, that's the amount of energy needed to remove the most loosely bound outer electron from a natural gaseous atom. What that means is the energy needed to make something into a positive ion, into a cation. When you make an atom from a neutral atom into a positive ion, what you are doing is removing an electron from the outer layer, the most loosely held electron. That makes sense. And to do that, it depends upon the size. So the bigger the atom, the easier it is. So as we remember, we went top to bottom, so as the atomic number increases down a group, the atom got bigger. So therefore, as the atomic number increases down a group, because the atoms get bigger, there's more shielding effect, so it makes it easier to remove those outer electrons. So the atoms that are the largest atom will be found over in the bottom left corner. The smallest atom will be found in the top right corner. So the smallest is going to be very difficult to remove an electron. The largest is going to be bottom down here. It's going to be very easy to remove an electron. So the first part is, as the atomic number increases down a group, the atoms get bigger, and that makes it easier to remove the electrons. And then as the atomic number increases across a period, the atoms are getting smaller, so therefore it's harder to remove those electrons. All right, so we have higher ionization energy. So again, copy those notes. All right, electronegativity. This term means it's the pull of an atom's nucleus on a shared pair of electrons. So it's the measure of the attractive force for a nucleus for a bonded pair of electrons, for bonded electrons. What this means, two atoms, if they share electrons or they get close to one another, one atom may be attracted to another atom's electrons. And that's what bonds happen, okay? For electronegativity, again, it goes hand in glove with the atomic size. The bigger the atom, the less pull that nucleus can exert. So the further that atom's electron, further those outer electrons are from the nucleus, the less that nucleus will be able to pull, all right? So there's one group here, group 18, which is not involved in this at all because, again, if we're talking about sharing electrons, we're talking about electrons in a arrangement that can be shared. Well, the noble gases, they don't share because everyone wants to get a stable octet, and the noble gases don't need that. So there's your two explanations for both the group and the period. Copy those notes. Okay, now that you have those notes, we're going to move on. So we're going to move on to this activity. It's the trends in the periodic table activity. And to do this, this is online. So this is over on the Schoology. So let me bring this in here, show you what we're doing here. So the periodic trends activity, you're going to construct and analyze three graphs. I've given you the graph paper. The graph paper already is set up. One's for atomic number versus atomic radius. The other one's atomic number versus ionization energy, and atomic number versus electronegativity. You need to look at the units. They are all standardized, so they're going to fit perfectly. I think one of them, the ionization energy, though, a 1 got cut off in part of the graph. So you may have to do that, write that 1 in. But anyway, I want you to use different colored pencils for each period. Remember, a period is the horizontal rows. When you get to the end of a row, you're going to switch colors. So you're going to do 4 periods, therefore you're going to need 4 colors. You do not connect the periods together. Sorry, you're connecting the dots within the same period. Do not connect period 1 dots to period 2 dots. Okay? So the first period is hydrogen and helium. The next element is lithium. There is a line between hydrogen and helium, but there is not a line between helium and lithium. There is a line between lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. That's all connected. But again, when you go to the next line, next period, neon to sodium, sodium and neon are not connected by the line. So what you're going to graph, you're going to use table S. You're going to graph atomic number versus atomic radius, okay? And So here's the first one. The first ones are atomic 1 and 2. That's the first period. Atomic numbers 3 through 10 are the second period. 11 through 18 are the third period. 19 through 36 are the fourth period, and that's all you're going to do. You are graphing ionization energy, electronegativity, and atomic radius. Those are the three things you're going to be graphing. All right. Furthermore, once you get those points plotted, all right, then after you get those points plotted, then I'm going to have you do some things. And so step 6 says draw circles around group 1 elements. Step 6b says draw squares around the points for group 2 elements. And step 6c says draw triangles around the points of each group 17 element. Okay? After you get that, there are questions you can do. All right? So when you get these, you're gonna get the graphs, and you'll be able to see what they look like. All right. If you have any questions for this periodic transactivity, please reach out to me, and I will do my best to explain it to you remotely, virtually, because we will be away from each other. It's a lot easier when we're here in person. But again, I can show you real quickly what they kind of look like. Kind of looks like that. That's what I'm looking for. All right. I want you to do that. I know you can print that out, but that's not what I'm looking for. I'm really looking for you to graph it, because it's a motor skills thing that allows you to start to look at period S closely and intently, and that's going to help you. All right. Best of luck. Let me know if there's any issues.